All right, today we are watching a program called Electronics at Work, and this was published all the way back in 1943. And if I'm to be honest, I didn't even know they had electronics back then, so this should be a good one. And this was published by the Westinghouse Electric Corporation, which is another old name I feel like some people might recognize. Westinghouse. That's a name that I sort of recognize, but don't actually know anything about, and I feel like we're about to learn why. All right, so we're looking at some sort of glass bulbs, probably light bulbs, through some sort of like kaleidoscope lens. Like I can't quite tell what we're looking at, but like we're definitely looking at something through a weird lens. This is like what the inside of like a fly's eyeball looks like. Yeah, already I'm starting to guess like what even are the electronics of 1940s? You know, like what electronics did they have back then? Like I'm seeing like glass tubes, you know, like I have no idea. If these aren't light bulbs, I have no idea what these are to be used for. So this should be a very interesting lesson on like the original electric devices pretty much. Like this should be very interesting, I think. Yeah, they're giving us like a tour of all these different like cathode tube things. I don't even know if that's the right term for it, but like I don't think they're light bulbs. I think these are all different sorts of things. I don't know. They might all be light bulbs too. They're all glass containers with something. I don't know. Oh, Electronics at Work. Interesting. All right, there's the title. Electronics at Work. A good font for it, too. I like this font. I don't know. The E is a little weird, but it's a good font. Hang on. The electronics is one font. The at is another font. And then work, I think, is a third different font. So I like the electronics font. I think that's a cool font. Oh yeah, presented by Westinghouse. So what was Westinghouse? I feel like I have to ask my audience that, right? Like I've heard this name before, and it seems like it's equivalent to like GM or something. Like it seems like Westinghouse was like a technology home consumer products company or some sort. Maybe we'll learn through this. I've heard that name before, and I'm curious. I'm curious what Westinghouse was or is. Maybe it's still around. I feel like during this time, Westinghouse was like a big recognizable brand name. Whereas at least I don't really have any association with Westinghouse. Like even though I recognize it, I still don't know what it really is.
Electronics is a science that applies these tubes to the service of man.
Electronics is a science that applies these tubes to the service of man. So these tubes, that's what we're talking about here. Electronics is the science of applying these tubes to man's service. So I have so many questions already, but I think they'll be answered if I just continue watching. Like what tubes? What happens in all these tubes? Like why are they all tubes?
Electronics is a science that applies these tubes to the service of man, to the speeding of production, to the winning of the war.
To the speeding of production and to the winning of war. So that's interesting. It's interesting how electronics, the very first like advertisement of electronics is as a thing that will help us win the war. Not even World War II, the war. You know, this was made, what, 1943, did I say? 47? But like this was very clearly inspired by World War II. And I think that's just a very important thing to understand. It's like the desperation that arose as a result of World War II resulted in advances in electronics. You know, very, very directly resulted in advances in electronics too. And I feel like we just need to appreciate that. Like, obviously, World War II was horrific and like the worst event in human history, but at the same time, it also pushed humanity so much further along than it otherwise would have been. And this is a perfect example of that. We are going to see the advances that electronics made, like the thing that I'm watching this video on, the thing that I'm recording this video on as well, all this stuff got its start right here in these glass tubes, you know, and the purpose of them was to win the war.
To understand how electronic tubes work, let's take a good look at one of them.
To understand how electronic tubes work. So it's so funny the terminology they're using even, right? Like to them, these are still electronic tubes. Like even that, like I really want to understand how they work, why they work, what these even are. They're not light bulbs, but they're electronics. So I'm so curious still. Let's keep watching.
One that's representative of its species.
A representative of its species. It's so funny how they had so many different types of glass tubes with different wires doing different things that they actually called this one one of a species. You know, like there are actually so many different species of glass tubes accomplishing so many different weird tasks that humans had never dreamed of doing before, that like they're all different species of tubes now. It's just that's a very interesting and enlightening term that they just used.
This is a diode, a typical two-element electronic tube.
The typical two-element electronic tube. Is this going to be a light bulb? Is that like the simplest version of this whole thing is a light bulb? Because I understand a light bulb. I don't quite understand what the rest of these tubes are. But let's see what this is.
Let's get inside it. In fundamental operation, it resembles an ordinary single pole.
Oh, here's another diagram. See, this is the real engineering aspect of this of the blue videos.
Switch. A switch that can connect, for instance, this battery.
Oh, look, a diagram. See, that's how I know this is a blue video. When there's a diagram illustrating like some complex scientific machinery, like this is a blue video for sure right here.
This battery and its motor load. One power lead comes to the anode, the other lead goes to the cathode.
Okay, like so far I'm following this, like this is basic electricity for you right here, but it's what's going to happen inside this tube that I'm real curious about.
When this switch is open, the contacts are insulated from each other by a vacuum.
Hang on. So the contacts are insulated by a vacuum, but electricity is still going to travel from the cathode to the anode. They're going to travel from one to the other. I'm doing too much to figure out the electricity of this all right here, but the electricity is going to travel through this vacuum from the anode to the cathode, or vice versa, however it works. And I think that's going to create light, right? Like you're going to have energy traveling through a volume. I don't know. Is this a light bulb? Is this like an LED or something? It might be an LED, but I don't know. I don't know.
Or by some inert gas inserted into an evacuated tube under low pressure.
Yeah, I understand that, but I don't know the special purpose of it. Let's see.
To close this switch electronically, all we need do is heat the cathode.
Hang on, to close this, you need to heat the cathode. So the opening is obviously in this vacuum tube. Like you don't have the cathode touching the anode, so you get no current flowing through the system. But the only thing you need to change that is to heat it up. That's interesting. So you attach it to a battery, which I assume, I don't know, there's two batteries here now. Yeah, this has already gotten like a little bit more complicated for me than I would prefer. But let's keep going. So what happens when the cathode is heated up? Like what? I just don't understand.
And give the anode a positive potential. Then here's what happens. As electrons are emitted from the surface of the heated cathode.
Okay, so the electrons are going from the cathode to the anode. I think I got that right.
Cathode, being negatively charged, they fly at tremendous speed to the anode. In this way, a current-carrying path is formed, which closes our electronic switch and permits our motor to operate.
Yeah, okay, so when this thing is heated up, the electrons are allowed to travel through the vacuum to the anode, which completes the current and allows things to go. I understand that, but I just don't get the purpose of the tube in this instance. Like that could just be replaced with a wire. I don't get what the tube is accomplishing that the whole rest of the system doesn't already have. I don't know, but maybe we'll learn.
You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus.
That's hilarious that I got it right, but the narrator had to specify that the electron flow is actually opposite to how it usually is. So actually, I think I did get it wrong. I just got lucky that in this situation, it's actually reversed for some reason. But that's interesting because it is reversed. Hang on, so which one's positive? Is the cathode positive or is the anode positive? I don't know. That's why I just said one or the other, because I couldn't really remember.
Now, at this point, you may ask, if an electronic tube is basically just a form of switch, why is electronics hailed today as the technique of a new engineering era?
See, I really like that question because that's literally what I said, right? Like, what's actually, like, it just serves as a switch then, you know? Like, it's just an on or an off. It's not like more complicated than that. So, what is the reason electronics? Like, how do you go from that tube of like electrons to electronics? You know, like, I still don't understand that. So, hopefully, I'm glad that they're asking that question though, because that means they're going to address it. So, let's keep watching.
To answer that question, let's review 6 of the basic things that we can do with this new kind of...
Geez, okay, 6 of the basic things we can do with this technology. I actually think this is really cool. I don't even want to try to guess some of these things because I feel like one is a light bulb, but the other 5 applications of this like completely escape me right now.
In the first place, we can rectify current with it, converting AC to DC.
You can rectify current with it? Interesting. So you can turn AC to DC or vice versa through just one of these glass tubes? That's interesting. I don't even know much. I don't know enough about electricity to really ask good questions in regards to that, but like that seems very impressive already that you can just transfer AC to DC through a cathode tube like this. I would not have guessed that, I guess.
We can do this merely by connecting an electronic tube in series with an AC circuit.
Electronic tube in series with an AC circuit. So the whole circuit is AC, but does this light take DC or something? So all right, let's keep watching.
As you study this circuit diagram, note that only each positive half wave of AC voltage will now produce a current. When the anode is negative, the electrons are repelled and no current flows. In other words, because only the cathode can emit electrons, we have here what amounts to a one-way street.
Yeah, that's interesting. I don't quite understand. So this is like filtering out the negative, so only the positive go through, or vice versa again? Like I'm not trying to keep track of that stuff.
We can visualize the result of the tube's rectifying action with the aid of these 2 oscilloscopes. The one on the left shows alternating current coming in.
Okay, yeah, so this is exactly what I thought, but again, I don't quite understand. I guess you're only getting the positive using this thing, whereas before you would get the positive and the negative. All right, so that would be the AC, is you'd get both the positive and negative, but then it converts it into DC, but that DC is only the top peaks of the amplitude rather than the bottom troughs as well. That's interesting. Because my thought of AC/DC, I don't need to explain my, yeah, never mind.
The one on the right shows pulsating direct current going out. The applications of this basic rectifying principle are many and important.
That is interesting because that's the next question I was going to ask is like, what's even the use of something like this? But let's see, I guess.
Here's one of them, changing AC to DC on the nation's electrified transportation systems. Here's another.
But I feel like, I guess they gave an example, but like they didn't explain at all. Like I don't get how the train switches from AC to DC or why that matters. Like that was an example, but it didn't illustrate anything to me.
Rectification for electroplating operations of all kinds.
See, this makes a lot more sense. They're electroplating stuff. They need to be able to control the current like that. That makes sense. I don't feel like I need an explanation for that. But for the train, that was just too general.
It's possible only with direct current.
Yeah, okay, see, it only works with direct current. So like that, I understand the application of it.
Still another example, furnishing DC in steel mills for the driving of variable speed motors, such as the one controlling this giant ladle, or the ones driving steel conveyors with such precise control of speeds that danger of buckling and tearing and consequent mill damage is eliminated.
Interesting. So switching from AC to DC eliminates the risk of your machines like buckling or receiving like too much electricity in one instant or something. I guess what they're trying to illustrate is that this tube allows you to choose which sort of electricity you want to send to your machine, which I guess is like the most important thing when it comes to electricity. So that's interesting. That's one good use of those tubes, I guess. And it's not even like an intuitive use. That is a really clever use of a glass tube, to say the least.
Electronic rectification is also helping to build American air power by making available record-breaking quantities of aluminum for plane construction.
That's interesting. So being able to switch from AC to DC also allowed us to manufacture more aluminum than we had been able to previously. That's a very interesting note. I wonder how exactly. I don't think they're going to illustrate it, but that's like a whole subject of a real engineering video right there for you. But it's interesting how not only did that allow us to have access to a new element or a new resource, aluminum, but having access to aluminum or more aluminum allowed us to build more planes for the war. Again, our advances in electronics were all, at this time at least, all made specifically with the intention of improving our ability to wage war. It's so shocking to see how like every comfort that we have today that comes through electricity has its origins in defeating the Nazis. It's just like, I don't know, it does give you some perspective on like the world that we live in. You know, like the computer I'm watching this on, the camera I'm filming this on, like all of this happened as a result of this war. And it's so amazing to see that stated during the time that it was taking place.
From Arkansas mud to American air power involves a complicated conversion of material.
From Arkansas mud to American air power. Like that's such a good phrase too. Like I love that our aluminum just came from Arkansas mud.
Before pure aluminum can be extracted from this bauxite ore.
Shout out to my Arkansas mud. Is there any mud from Arkansas watching this video? Shout out to you guys.
Direct current must be applied in a vital reduction process. To obtain that direct current from AC transmission lines, the ignitron rectifier is used.
Hang on, what was this thing called? The ignitron rectifier? That is like the name of a transformer, you know? Like we're a bit above my pay grade now.
This Westinghouse electronic development changes vast quantities of AC to DC with higher efficiency than...
No way, hang on. Are these the things that are on like telephone poles? Like are these like the weird little buckets or I don't even know what to call them, but I feel like I recognize these. These are on telephone poles, I think. Maybe they're not. Maybe there's something different, but like these look like the things that are on telephone poles. But that's also interesting how he said this is what Westinghouse does. So I guess Westinghouse made some sort of electronics, like that was their thing. That's interesting.
Any similar type of conversion equipment. Today, it's the main source of current supply for the nation's great aluminum industry, an industry that has achieved a miraculous expansion to meet the demands of a world at war.
Yeah, you know, I should watch a video on aluminum eventually here. I do have, I think, at least one, maybe two programs specifically on aluminum. So maybe I should watch those soon as well, because I'm picking up on aluminum being like the metal that helped the war effort more than any other. Maybe steel, but aluminum seems to be like the new tool that helped win World War II.
Magnesium from seawater is another achievement of industry under the stress of war. Ignitrons used in the extraction process speed up the delivering of incendiary and demolition bombs to the centers of Axis production.
Well, I'm glad this technology also allowed us to make more bombs. That's like, oh great. That's exactly what everyone who did research into this wanted, but that's like the least good application of this sort of knowledge. But I think that's also important. Again, like the scientific breakthroughs came not because people were curious about electrons, but because people needed to kill other people, you know? Like that's the whole human history right here. All technological advancement has taken place in order to gain advantage over your enemies. You know, like that's what we're seeing here is no different than like the first spear being made, you know? Like we're getting to see the advancement of human knowledge through this as a result of war. There's so much to unpack here.
Still another example of electronic rectification at work is the precipitron, a device...
The precipitron? Yeah, we really are just in Transformer name territory now, aren't we? The precipitron. Let me try to guess what the precipitron does. I think you're trying to take moisture from the air and have it precipitate out, but that would be more of a condensatron than a precipitron.
At work is the precipitron, a device for cleaning air electrostatically.
Huh, a device for cleaning air electrostatically. So I guess it probably picks up dust by having something that's statically charged and blows air over it, and the charge attracts the dust or something. That's interesting. That's not what I would have predicted for something called the precipitron. Can somebody, are there any Transformers fans out there? Is that the name of a Transformer, the precipitron? If not, you guys got to get on it.
This diagram explains how the precipitron works.
I feel like this episode has had more like crazy machine terms than any other episode in the Blue I've watched so far. You know, like this, the rectifier, the precipitron. I feel like there are even more that I already have forgotten too. Like the fact that we're still talking about applications of the rectifier. Like that was the first application in 6 that we're going to be touching on. So like it's so amazing. There are so many applications for electronics, and it's so funny for me to be realizing that only by watching this, you know, only by seeing every different place a rectifier, a glass tube called a rectifier can be used. It's just, I don't know, I am being overwhelmed by how applicable all this information is.
The rectifying property of electronic tubes is used to apply a potential of 13,000 volts DC to tungsten wires.
13,000 volts DC to tungsten wires. That seems pretty intense. Oh, is this still the precipitron? Wow, that is a big charge. So I guess they are trying to pick up the dust using a charge. Maybe not, but I think that's where they're going.
And 6,500 volts DC to collector plates. As incoming air passes through the field of these wires, each particle of dirt receives a positive electrostatic charge.
Okay, yeah. So they are trying to collect the dust based on charge. So these wires are supposed to give them a positive charge, and then with that positive charge, they'll be attracted to the negatively charged collector sheets. That's interesting.
When the positively charged particle reaches the collector chamber.
Dude, again, what a good animation. This is like, again, just on par with real engineering in terms of like the purpose and function of the animation in the program. Like this is a real engineering animation right here, like hundreds of years before Brian ever started real engineering.
The collector chamber is attracted to and deposited on negative plates.
That's funny, yeah, they are actually collecting specifically on the negative ones too. Very good animation, again, very accurate information here.
In this way, air is cleaned so thoroughly that dirt particles down to a 1/4 millionth of an inch are removed.
Do we still use these? Like, are these machines still like applicable to our times even? Like I don't have a, what was it, a precipitron? I don't have a precipitron in my house. Am I just breathing in dust, or is this like an industrial dust catching machine? You know, like what's the application of this? Is this for like a factory that makes dust, or like is this for a consumer household thing?
This is a vital advantage today, not only in homes and public buildings, but
so this was made to be a consumer product. That's interesting. I wonder if this is just like how regular air purifiers work. Probably, this is probably how air purifiers work.
but in industrial plants of all kinds. For instance, in plants manufacturing delicate instruments where air cleanliness is necessary for precision work.
Wow, see, that's interesting. They're even going into like the examples of like why this thing would even be like, I feel like we're 3 examples deep now. Like we're not even supposed to be learning about like this factory. We're supposed to be learning about the applications of these electrotubes or whatever. But like here we are learning about why the precipitron is important for this factory, because they can't have dust in their factory with all these small parts. It's just like we are learning some very, very specific information in this one. Also, this is interesting. Let's just look at the hands that are handling this little instrument right here. Based on the color of the nails, I'm going to assume this is a woman, which is, again, interesting. We are getting to see a woman in a very, high-tech advanced factory working on some sort of instrument. I guess what's important to remember is, again, this is during World War II, right? That's what we were all taught, is that during World War II, all the men had to leave, so all the women came into the factories and started working. World War II is really when women entered the workforce in bulk, and I think that's what we're seeing right here. We're seeing a woman working in a factory. It's interesting that like that history lesson that I learned in high school is actually reflected in this program right here in front of us. It's always interesting when that happens. It's also funny to note her nail is actually chipped a little.
In workrooms where optical systems are assembled for a host of military purposes.
Yeah, for a host of military purposes. So yeah, look at all these ladies in this factory. Like this is a woman-operated factory for the war specifically. That's crazy.
In inspection rooms where minute parts must be closely examined under high magnification. Air cleanliness.
That was real cool. We were seeing the little parts that needed to be like inspected under magnification. Like, does anyone know what these are? They kind of look like springs. Like, what machine were these parts being used for? I'm so curious about it all, you know?
Air cleanliness is vital too in film developing rooms like this one.
Oh, in film developing rooms. That makes sense as well. See, it's funny how we're now talking about the applications of a machine that's like, I guess it isn't electronic. It's just like, I feel like we're kind of getting sidetracked. Like, we're not learning the application of these tubes anymore. We're just learning why people like to filter their air, you know? Like, I understand, okay, filtering air, that's good for photography. Filtering air, that's good for like factories that can't have a lot of dust or whatever. But the point of this program is to tell me how electricity can filter air, not why filtering air is important to people, you know? Like, I feel like we've gone one step detached from the purpose of this program now.
To understand how electronic air cleaning helps here, let's go aloft in a reconnaissance plane.
Yeah, like now we need another example of how electronics can clean our air. Like, can't we just get to the other applications of electronics? Like, I understand how this works, so we can move on, you know? But I guess here we go. Let's learn another example.
Click. 5,000 feet above the earth, a camera shutter opens and closes. Scores of square miles of enemy territory have been squeezed down into an image on a photographic plate.
Scores of square miles have been squeezed down to a square inch on a plate. So is this a photograph of like Nazi Germany from above? Like, is that what they're saying through that? Like, this is actual enemy territory? That's interesting. Can anyone identify the German city this is based on the aerial photography? I wonder.
An image measured in inches instead of miles. On this photograph, a city might be covered by a tip of a finger. A speck of dust could hide a Nazi aerodrome.
Oh, okay, I get it. I understand why they're talking about this now. Yeah, a speck of dust could cover up some very important information on a photo like this. So they need to make sure there's no dust in the camera body or whatever so that it doesn't clog up the image. That's just like, I can already see what they're doing. That's funny.
The rectifying tubes of the precipitron help make sure that dust.
The rectifying tubes of the precipitron. I can't get over the terms that we're learning today.
Doesn't sabotage military photography. Now, so far in this film, we've discussed only one of the basic things we can do with the electronic tube.
Yeah, that's what I was saying. It's like we're almost halfway through and we've only hit on one. And it's like one that I'm not even very familiar with. Like, I'm glad I learned about rectification, but I feel like there's a lot more we got to get to still.
We can use it to rectify. The second basic thing we can do with it is amplify.
Amplify, that's interesting. So I wonder if on one side you'll have the cathode, that's the thing that's sending electrons, and on the other side you just have like an oversized anode or something that picks up on the signal from the anode, but more so. I don't know. Let's see how you amplify electrical signals using a glass tube.
Here's how. Between the cathode and the anode of the two-element tube, which we diagrammed a while ago, we now...
I love how they say a while ago, like it's already been like several minutes since we had this explanation. For me, recording, it's been like half an hour already, so yeah, I do need a recap.
To this grid, we connect an input of some weak voltage which we wish to amplify, perhaps that of a faint radio.
Hang on, we place a grid. So is this like a metal sheet or like something like that? I feel like that's what they're getting at. And this grid is connected to an input or an antenna. That's interesting. So I really have no idea where this is going.
Wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens.
Oh, interesting. So the antenna brings in a signal, and that signal gets put into the grid, and then the grid is going to release electrons from that signal, and then that's going to be picked up by the anode. Is that how it works? Oh, okay, so there's already a big signal, but then when you input the signal from the antenna, maybe that amplifies it. Let's just see. I like to try to guess, but I think for your guys' sake, we're just going to listen to the explanation.
Every time a negative potential is impressed on the grid, even though it be very minute, It has a large effect in reducing the number of the negatively charged electrons which would otherwise.
Oh, interesting. So the grid acts like a filter, right? The grid filters out the negative charges that are not being sent through or something. And I feel like the grid determines what negative charges are filtered out based on the signal coming in from the input from the antenna, right? The antenna receives an electrical signal, and then that signal is communicated to the grid through the wire. And then whatever that signal is, the grid determines that it doesn't let in the information that disagrees with that information. And then the only information that gets through, or the only electrons that get through, are the electrons that line up with the same thing that came through the grid. So you end up getting only the message that the grid wanted. That's my guess, but I said I'd let them explain it. So let's keep learning.
Keep flying from cathode to anode. Conversely, when the grid is positive, an equally large effect is exerted in increasing the flow of electrons from cathode to anode. The important thing to note here is this. A small amount of power applied at the grid is amplified into a large amount of power in the anode or work circuit.
Interesting. I wonder why that is. I don't quite have a full understanding of this one yet.
This amplifying property of the three-element electronic tube is put to work in innumerable.
Amplifying property. I just don't understand how the signal was amplified. I don't know. I feel sorry for any of you who perfectly understood that explanation, but I don't quite understand.
Westinghouse electronic amplification now helps provide radio and radio telephone contact between airplanes and control stations on the ground.
Yeah, even though I don't understand it, I do understand why that would be important. Increasing the power or distance that your signal gets sent just is understandably important, especially when you're flying planes or operating over a large area. It makes a lot of sense that making your signals go longer is an important thing. So I do understand the application of this, at least.
Between ships and their communication bases, both afloat and ashore. Between individual tanks and their tank force commanders.
Dang, look at all these tanks. Were these tanks communicating with each other? I want to know that. Like, did they all have walkie-talkies and they were, like, talking to each other? Like, how were these tanks communicating with one another? I don't know. I honestly did not think these tanks would be. I thought they would all just get their, like, directives and then just, like, go out and do their thing. I don't know. I just did not expect them to be talking to each other.
Between individual tanks and their tank force commanders. Between firing line and headquarters. Between Seadrome lights and night-flying pilots who can turn them on by radio signal.
Did he just say Seadrome lights? That's interesting. So those are little buoys that turn on remotely. That's interesting. That's probably for like shipping and boats and whatever. That's interesting. That's a good application.
In the field of power engineering, electronic amplification permits the measurement and analysis of minute voltages, stepping them up to the point where they can be seen and interpreted on oscilloscopes.
That's funny that one of the applications of the amplifier is just that it amplifies things so that we can read them better. That's just like the most simple and obvious thing, but I guess like it needs to be said.
When this giant rotor is completed, its precise dielectric balancing will be made possible by amplifying tubes.
That's interesting. I'm curious how. Like, again, they said it will be made possible with these tubes, but they didn't explain how. Like, how will an amplifying tube make us capable of measuring this, like, steel hull better? Like, I just don't know. I don't understand that either, but you know what? I'll take their word for it.
Testing of these propellers for vibration fatigue will also be facilitated by electronic amplifying tubes.
Testing these propellers for like their fatigue from vibration, and you use an amplifying tube, like, I'll be honest, I don't get it. I don't get that one. Like, that doesn't really, I just don't get where you're using an amplifying tube in that situation.
Up to now, we've considered two of the basic things that the electronic tube can do. It can rectify, it can amplify.
Oh, are they going to say now can it, like, I don't know, insulate or something? I don't know. It seems like they're setting up something opposite from rectifying or amplifying. I wonder what that is.
A third thing it can do is generate.
Oh, generate. Wow. These things can generate electricity? I doubt that. Let's see how they explain that, but I have my doubts.
The term generate in this connection is meant in a general rather than a technical sense.
Oh, okay, in a general rather than a technical sense. That's so funny that, like, they knew that I was going to pick up on the doubt of, like, the fact that this tube can generate electricity. Like, that is a very big claim to make. So I'm curious what they really mean, because I just don't know what they mean in the general sense of generate.
A triode is connected for oscillation in the way shown here. The system then becomes capable.
All right, so we have a pretty complex circuit already. Not complex, but like it's a lot to take in. Like I gotta spend a second to look at, all right, we got a DC source, we got a battery, we got a coupling coil, we got an AC input, and then we got some coils over here. I don't know. Like this is a lot for somebody to take in one moment.
Becomes capable of changing direct current into alternating current. Note that what we're doing in this case is amplifying in the usual way and then feeding back to the grid part of the amplified voltage. Continued repetition of this feedback results cumulatively in a strong alternating current. This electronic means of generating alternating current is important.
Electronic means of generating alternating current. That's, again, like I feel like we already touched on that with the rectifier, but like, I don't know, I just feel like I'm just getting so confused now. There's so many like tasks. This really is exemplifying how complex electronics were and are. Like the fact that we have these little glass tubes, but like boiled down to like the size of a computer chip is just crazy.
Because it can produce very high frequencies up to millions of cycles, far beyond the range of ordinary rotating equipment. A familiar application of this is the radio transmitter. This modern transmitting room of Westinghouse station KDKA.
Transmitting room of Westinghouse. See, I feel like we're getting a real good tour of like the Westinghouse like factory or whatever, their headquarters at the very least. And I think I am actually getting an understanding of what this company did. They were clearly involved in the electronics industry. Westinghouse might even have been like the first electronics manufacturer. Like that's kind of what it seems like based on this.
KDKA is a far cry from the pioneering equipment of its famous predecessor.
Its famous predecessor? Who was Westinghouse's famous predecessor? Like they say that as if like the audience just knows, but I don't know because I'm like 100 years in the future, I guess. But I'm just like, who is it? Who is the predecessor of Westinghouse? I don't know.
Is a far cry from the pioneering equipment of its famous predecessor.
Pioneering equipment of its famous predecessor. Who is Westinghouse's famous predecessor? I don't know. It must be GE.
This scene reproduces an historic occasion. The first time a radio transmitter was used for large-scale public entertainment.
The first time a radio transmitter was used for large-scale public entertainment. So again, another little historic moment right here that we get preserved for us.
This is station KDKA of the Westinghouse Electric and Manufacturing Company.
Westinghouse Electric and Manufacturing Company. So yeah, they pretty much were General Electric. GE, not GM. I think I've been saying GM, but GE.
We are about to begin the reading of the presidential election returns between Warren G. Harding and James M. Cox.
Dang, that's crazy. The first thing they said for the first broadcast of the radio, whatever, is the presidential election result. That's so crazy. And who was elected? Hang on, I gotta go back.
We are about to begin the reading of the presidential election returns between Warren G. Harding and James M. Cox.
Dang, that's so funny. They're about to start reading the election returns of Warren G. Harding versus somebody else. It's funny because I don't recognize the other name. Like, I already know who wins this election just based on those two names because I only recognize one of them. It's funny how during this time we were literally seeing the people who did not know the answer to that. You know, like it's just funny. It's another funny aspect of watching these historical programs is that like there's just information that these people don't know that to me is literal like ancient history.
Presidential election returns between Warren G. Harding and James M. Cox. Stand by, please.
Dude, I wonder where America would be if it was Cox instead of Harding. That's actually funny that we had an election of Cox versus Harding.
Here is a new, less familiar application of electronic high-frequency generation. High-frequency heating of 200,000 cycles per second is now used to flow tin as the final step in the electrolytic plating of steel strip.
The electrolytic plating of steel, that's interesting. So I guess this is just another application of the amplifying. That's just, all of these examples, to be honest, are very counterintuitive. Like I have no idea how a generator is going to help add tin to the final layer of this steel thing. Like that's just, I don't know. I feel like these examples are good. They're definitely useful, but I don't really understand them.
After steel strip comes from its electrolytic tin plating bath, it first passes through a washer, then between hot air drying jets. At this point, the steel strip has a coating of tin that is relatively dull and porous. Next comes a vital step. The strip is raised to the top of the heater unit housing, inside of which is a series of high-frequency coils. As the strip comes down through these coils, induced electric current causes heat, which flows the tin almost instantaneously, greatly improving its structure as a protective covering.
Huh, that's interesting. So they put the tin on in some other way, and it doesn't really work that well. It's porous or whatever. And then you run it through this electrical generation thing, and it just evens out the tin coating. That is interesting. I kind of wish we had an explanation for how that happens, because I am trying to use my imagination and it's not working.
Here's the result. Tin plate that is mirror smooth, free from porosity, so perfect a protective covering that 1 pound of tin can now do the work of 3.
Wow, that is impressive. See, I do love hearing stuff like this. Like, this advancement allowed us to use so much less tin to accomplish the same thing. It's just like, it helps understanding how all of these advancements actually, improved our society and our industries. It's cool to learn that, we used to be so wasteful, but we actually did discover methods of improving our efficiency. It's just this is the era of that taking place, of all these big advancements that actually improved our lives. It's just it's so wild getting to see these changes that still affect our lives today and make our lives better today. It's really incredible.
Note the horizontal bars in this close-up. These are parts of one of the high-frequency coils that affect the tin flow.
Okay, interesting. So these are the high frequency coils, and then the steel is run between the coils, and then I guess the electricity either heats it up or has some effect on it that it causes the tin to flatten out. That is interesting.
If you look closely, you can see the difference in texture between the porous tin entering the top of the coil and the shiny flowed tin leaving at its base.
Oh wow, that is interesting. So the tin coming in is kind of rough up top, it's just like a dark gray, and then the tin coming out on the bottom is kind of hard to see because it's so light, because it's so reflective. That is really impressive that it just happens over this 2-foot span of coils. It doesn't take a very long exposure or a very big exposure, but it happens anyway. That is incredible.
And these are the tubes that generate the high-frequency current which makes the entire process possible. Another important result of this new Westinghouse electronic process is time saving. Tin can now be flowed at a rate of more than 1,000 feet a minute. Here's another example of where electronic high-frequency generation is doing a job today.
Electronic high-frequency generation. So I still don't understand what we mean by generating. I feel like that could have been explained better.
Dielectric bonding of plastic and plywood sections in a matter of minutes instead of days.
Electric bonding of plastic and plywood components? That I have never heard of before. You can electrically bond plastic to wood? Excuse me? I feel like, am I the only one learning this for the first time? You can bond, I gotta learn more about this.
As a result of this application, plywood-constructed PT boats can be produced more speedily.
That's so funny, so interesting. So you can bond plastic to wood using some high-frequency generator, and that would be the wood that we would use to make boats. Which is so funny because during this time, I imagined we would be using steel for our boats, right? But I guess we were still building our boats out of wood sealed with plastic. That's crazy.
Dielectric heating also cures intricate plastic forms faster and better. Here, a dielectrically cured plastic piece is being given a stress analysis. Carrier current relaying also applies the electronic principle of high-frequency generation.
Yeah, we're getting a lot of examples, but we're not getting a lot of explanations for these examples, which I'm fine with because I don't think I would even understand those examples or those explanations anyway. I have nothing to say so long as all we're doing is looking at examples every 5 seconds.
Part of the equipment that does the work. This equipment makes possible an enormous increase in the speed with which transmission lines can be cleared of faults.
This is interesting, though. I do like hearing how each one of these things improved our society and technology. All of these are so unexpected but so impressive at the same time.
Its effect is to increase the load carrying ability of a system up to 50% or more. We've now illustrated 3 of the basic ways that the electronic tube can be put to work.
All right, these 6 ways are definitely going to be on the test. So you guys got to pay attention. We got rectify, we got amplify, and we got generate. That's half of the test right there. What are the rest of the 3? Can I guess the rest of the 3? Probably not, right? I couldn't even guess any of these, to be honest. So no, there's nothing in my mind that I could use as a guess. So let's just keep going.
It rectifies, it amplifies, it generates. And here's a 4th thing it does. It controls.
It controls. That's interesting. I again am struggling to come up with a way for a glass tube to control stuff. But let's just learn.
This diagram illustrates one of the principal mechanisms of electronic control.
Oh, maybe if there's like not enough like current to pass through this vacuum, it won't. So like this is a good control. Like only a signal will be sent if there's enough, energy to overcome this vacuum gap. Maybe that's how it controls.
We use the grid here not to amplify a weak signal, but to control the flow of power to a machine. To do this, we connect the control circuit in such a way that it becomes a function of temperature, speed, time, or any other variable.
The control circuit so that it becomes a function of temperature, speed, and time. So, all right, so there's a thing that is supposed to control how much energy a machine receives based on one of these qualities. Okay.
As a result, grid potential is varied, and the work circuit is automatically closed.
Okay, so interesting. So if like this machine gets too hot, something will trigger in the control circuit to turn off the tube, and then that will stop sending electricity to the machine to allow it to cool off or something along those lines. I think that's the application here.
Modified, or opened. And we can do all this with split-second timing and incomparable precision. Take, for instance, this electronically controlled spot welder. Without sound, without friction, without flame, electronic control on this equipment makes
That was pretty impressive.
and breaks contact with split-second timing.
Wow, that's so funny. So they actually have lights attached to each one of these like electric avenues so that you can actually see what the machine is doing based on which light is lit up. That's such an old-timey way of electronics, but again, that's literally what we're watching. I forgot that was like an aspect of old electricity of like you'd have lights turning on all over the place to tell you what was happening, but like that is really cool. I really do appreciate that. And I feel like I actually understand this part as well.
Seam welding, too, is electronically controlled.
Dang, look at this woman, this queen, straight up seam welding. Like, oh yeah, shout out to her.
As a result, plane parts today are being literally sewn together with electric current as thread.
That is crazy. We're actually sewing metal together using these things. Oh wow, that is crazy. That's like that's definitely another like technological advancement for sure.
But welding, of course, represents only one opportunity for electronic control.
I don't quite get how the control plays into it still. Like I guess it's like controlling for temperature or pressure or something, but I don't know. I don't quite get it.
Automatic stepless regulation of motor speeds is another application. Without the smooth acceleration which such control makes possible, delicate materials, such as the capacitor windings being handled here, might be broken under the shock of starting and abrupt speed changes.
Okay, interesting. So I feel like they also manage like the speed at which things go. So that it is interesting that they do control things. I wish I had a better explanation because I could not explain it to you guys how this works, but I feel like I do sort of understand.
Now for still another basic thing that the electronic tube can do. It can also serve as a bridge to transform light into electric current.
Transform light into current. That's interesting. That's actually really funny because that's the exact opposite of what I guessed, right? I guessed that one of the applications of this would turn an electrical current into light. That's a light bulb, but I guess we're doing the opposite. I guess we're taking light and we're transforming that into a current. I'm very curious about that actually because that's like what a solar cell is. So let's learn how we transform light into current, shall we?
Here's how. We replace the ordinary heat-activated cathode of a two-element electronic tube with one made of photosensitive material.
Photosensitive material. So this is no longer heat activated, it's photo activated. That's interesting.
Light can now replace heat as the stimulator of electronic emission.
Huh, that is interesting. I never really thought about that. I need to know more about this cathode thing, but I think this is really interesting, actually. Honestly, this is like me learning magic. Like, if you ever wanted to know what a real smart human learning magic looks like, this is it. Like, I am actually trying to understand the magic that is electronics right now.
The stronger the light, the greater the electronic emission, and consequently, with the aid of an amplifier, the more power flowing through the work circuit.
Interesting. So the sunnier it is, the more activated the cathode is to allow the transfer of electrons to the anode, or vice versa, whichever one they are. But that's interesting.
This is important because it means that photoelectric tubes can function as light relays and so be given an almost infinite variety of jobs to do. Scanning the soundtrack of the talking motion picture film you're listening to right now is one of them.
Scanning the soundtrack of the motion picture you're watching right now. That is interesting. Oh, okay. So that's really interesting. So hang on. So you have this thing that's capable of detecting the level of light that it receives. And the level of light that it receives determines the strength of the electrical signal that it's sent. So yeah, you do have this thing that takes in the light information and translates that into electrical information, which we can probably transfer back into like human information somehow.
Another is the television camera. The iconoscope used in this camera is merely a special form of electronic.
Whoa, this is so interesting. This is like true like science magic right here. So this is a television camera like broken down into its like most basic like constituent parts. That's like I need an explanation for this as well. I need some maker YouTuber to make a camera like this as well. I think this is like a really good challenge for like a maker out there.
Product and process control is still another application. In this plant, a phototroller automatically...
Oh, that's interesting too. So this thing sees how much light is reflected, and based on that, it knows a quality about the product. That's interesting. That's like another industrial application for this technology. This is interesting. Even though I don't quite understand it, I am capable of appreciating like intelligent design. Like I don't understand how it works, but I understand what the effect of it is. And then somebody was able to understand the effect and come up with an application for that effect. Like that's how it all works. Like it's so interesting.
Stops a conveyor belt every time a lightning arrestor comes to its point of inspection. Here, a Westinghouse electronic eye inside the metal housing spots pinholes in metal strip as it comes from...
That's cool too. A Westinghouse electronic eye spots pinholes. So yeah, really will just react to the amount of light, and then it can tell you, oh, there's light getting through because there's a pinhole here. Like that is good. That's good. I understand the application at least.
From the rolls, automatically operating a relay that rejects defective sections, dropping them out of the production line without a moment's loss of working time.
That's really interesting. Yeah, that we have these things detecting errors, and then we have these other machines hooked up to the things that detect errors to change the trajectory of the product to throw it into the trash instead of keeping it along the assembly line. Like that's very high level industrial engineering right here. Like that must have felt so advanced for the people who set that up. Like, oh yeah, it automatically discharges the ones that are bad. Like we don't even need to look at them, and we don't need to get rid of them. It looks at them for us, and it gets rid of the bad ones for us as well. Like that must have been such an advancement for that factory.
One of the most important basic things that the electronic tube can do...
Okay, we are 5 for 6 now. Are we going to get a light bulb, or is there going to be like something completely unexpected? Like I will feel so dumb if they don't even talk about light bulbs, because that's the only thing I have in my brain that this looks anything like, you know? Like this looks like a light bulb to me. So I have to imagine that's the 6th and final application for one of these. But I don't quite know, because I don't know if a light bulb counts as an electronic. I guess it does. I guess a light bulb is like the original electronic. So you know what? I do support that. I feel like that should be the very last example. But let's see what the last example actually is.
Remains yet to be listed. Besides transforming light into electric current, it can also transform electric current into light.
There we go. Yeah, oh wait, I got it right. I predicted the last one first. That's all right. I'm not proud of myself because a light bulb is a very common thing that everyone watching understands. So I feel dumb for being proud of myself for guessing that correctly. I'm proud. I still am proud. I don't know. I feel like that wasn't a given. Like based on everything else we learned, I feel like the fact that they saved this one for last really made me start to worry. I was sweating it there for a second. I was starting to think that I didn't actually understand light bulbs. I'm glad we're talking the same language now. I feel like I don't even need to watch the explanation for light bulbs either. Like I actually understand that. Like that is a light bulb is like the simplest version of this cathode tube thing, which is funny because on the one hand, I feel like that actually has fewer applications, right? Like just making something turn on a light isn't as amazing as having it amplify or generate or control, right? Like I feel like those are the actual notable discoveries in electronics, is the fact that you can rectify and amplify and whatnot. I feel like producing light is like a pretty minimal task compared to the rest of these.
The cathode ray tube is an application of this
A
property.
cathode ray tube. I feel like that's what I've been calling all of these. Maybe that's a very specific sort of tube, but that's, again, the term I have in my mind for tubes like this.
Through the
Dang, look how big that light is. That's like, that is the straight up the biggest light bulb I've ever seen. Right? Like I've never seen a light bulb bigger than like some guy's torso.
of this tube, an electron beam is able to recreate an original image on the screen.
Oh, it's a different type of light bulb. Interesting. So that was like a TV light bulb? Interesting.
The electronic X-ray tube indirectly.
Dude, this is an electronic X-ray tube. See, this is what I love. Is again, it's just a glass tube. Like this looks like something straight out of like an alchemist's office or something. But no, this is an X-ray tube. Like, oh my God, this is so interesting. It's so amazing is what it is. Because when I hear X-rays, again, to me, that's like magic. You know, like there's no way you can explain X-rays to me that doesn't feel like magic. But then seeing this glass tube with like a metal in it as an X-ray tube, like that, like it makes sense. Like it actually reveals the true like origins of these amazing machines that we take for granted nowadays. Like I really just appreciate getting to see stuff like this. Like this is such a good simplification of such a complex device. I really do appreciate it. So let's actually learn how an X-ray tube works.
Also transforms electric current into light, and by its effect on photographic plate, into light images. Here's how an X-ray tube works.
Oh, this is cool. So for a second, I was worried that they were just going to skim over that example like the rest of them, but no, we're actually getting a full diagram. I knew this was too interesting of a thing for them to not give us a diagram on. So yeah, let's learn.
A high potential ranging up to 300,000 volts.
High voltage DC on either side of this. That's interesting. This is already like so interesting. Like an X-ray tube is just like a big empty glass bulb in the middle of this glass tube. It's just like, I don't know, like the wonder of technology is so much cooler than magic, you know? Like this really is, it's amazing that this all works. Like this is all true and like we actually have like X-rays because of this, you know? I'm just, this is so amazing.
Volts or more is applied between the anode and cathode. Electrons are emitted by a focusing cathode.
By a focusing cathode. Electrons are emitted by a focusing cathode. Okay, I have to say that to myself to understand.
Due to the extremely high voltage, the electrons hit the anode with tremendous impact and cause the emission of waves of exceptionally high frequency.
Huh, so all right, so they're shooting electrons so quickly at this one thing that this thing actually emits light energy of its own, and the wavelength of that light energy, I guess, is X-rays. That's interesting.
These high-frequency waves do three useful things. Penetrate, excite fluorescence.
See, this is just like, again, like, it's so simple. Like, it's again, I think that's why it seems like magic to me. Because, like, so hang on, you're just shooting electrons at this one thing, and then, like, X-rays come out. And, like, that's it. Like, that's all it is. It's not, like, the most complex explanation ever. It's just like, yeah, we're shooting them, and they're coming out. Like, it seems so simple that it does seem like magic.
Fluorescence or affect photographic plates.
Oh, but this is interesting too. So, all right, so that thing produces X-rays, but it doesn't make the X-rays that you actually see. The X-rays that you see, we have a paper with a film on it, and that film is sensitive to the X-rays, so that when you shoot X-rays through your bodies, the hard parts, like the bones, don't let the X-rays pass, but your skin does let the X-rays pass. So you end up with a film that are exposed in the places where X-rays were allowed to pass and are not exposed in the places where your bones were, which is just very interesting. It's so incredible that somebody came up with this. But yeah, this part I definitely do understand.
As a result, doctors can now study human internal organs by means of the fluoroscope.
The fluoroscope. I really hope all of you guys have been paying attention to all of the instruments and all the names of all the instruments they're using in this video, because this is like a wealth of like amazing, weird, old industrial instruments and tools, I have to imagine.
Or by means of radiography, they can photograph them.
Radiography. That's funny. That's another good term.
Industrial X-ray today is also playing a vital role, detecting porosities and fissures in welded metal seams. Examining...
It's actually so funny to think of people in factories taking X-rays of like wheel hubs or whatever just to find like errors, you know? Like it just seems like X-rays are these things that are so important to human medicine that it's almost like comical that we use them for other stuff as well. You know, like this life-saving technology is used on like this metal just to make sure that it's all right, you know? Like it's just, there's something funny about using an X-ray for something other than like a person who needs something with their own body helped, you know?
For invisible internal weaknesses. But X-ray isn't the only example of electronic usefulness in the conversion of current into light. The whole...
Oh, hang on. What is this woman doing? This is a pretty cool demonstration right here. I feel like I see the most insane science demonstrations in these old programs as well. Like, why don't we have stuff like this now? Like, it blows my mind that I will see stuff from the 40s that still impresses me from a technological standpoint, you know? Like, I feel like I should not be impressed by anything I see in any of these programs. So what is this thing? Why is it turning on the lights, you know? It's just like, this is cool. I don't know. Why don't we have these, you know?
The field of modern fluorescent lighting represents another application. So does the field of ultraviolet radiation. Harmless-looking tubes like this one have a deadly effect on bacteria and other forms of
That is interesting. That's like the first time we were putting it together that we could use like UV to kill like microscopic organisms. That's again like that is such an important human advancement. Like the number of people who have been able to drink clean water because of what we just saw, like the fact that this all just happened right here in front of us. You know, like the world is changing right in front of our eyes watching this sort of stuff.
Microscopic light. In this demonstration, Parmesia rather than bacteria are about to be subjected to Sterilamp rays.
That's so funny how they specified that these are not bacteria, the parameciums. It's just like, especially in a program about electronics, like that's just not very important information at all. But I appreciate it nonetheless.
Notice what happens. The Sterilamp today is becoming increasingly important, both as a servant of public health and as...
I think it's so funny that we're just looking at shots of dead microscopic organisms. Like, yeah, this is proof that the UV lights actually work, but it's just like, it's just things sitting still. Like, these aren't recognizable things to human eyes, right? Like, these are microscopic one-celled organisms. So, like, we're just looking at shapes staying still, which is funny from a visual perspective, but makes a lot of sense from the story perspective.
...as a device for the preservation of perishable goods.
Preservation of perishable goods. See, that's another good application. That is something that this program has done very well, is actually tell you things that do sound important.
So many and so varied are the applications of electronics that a single film like this can mention only 1 in 1,000.
That a single film like this can... That is true. Like, there are so many applications of all these things that, like, every example he's given is just one little thing within the bigger picture, you know? That is very true. Electronics, especially in the time since this was made, have expanded to encompass so many different tasks and capabilities that, like, really there is no way to give an example for everything.
We haven't even mentioned, for instance, radar. The electronic development that helped save Britain during the decisive weeks of the German aerial blitz.
Dang, was that an air fight between a plane and a Zeppelin? That was crazy. It's a crazy shot. Yeah, that was just a balloon that plane knocked down. Some crazy war footage in the middle of this electricity program for us.
Here's what happened. Ultra-high frequency waves were broadcast into the skies from English defense stations. When enemy planes approached in the darkness or in the fog, these waves would reflect back to the transmitting points.
Yeah, again, this is just nailing home how like all of these advancements took place not only during the war, but because of the war. You know, all these technologies have a war application to them. And that was the first application of most of them. It's just like watching this reminds you of like how desperate all of humanity was during World War II. Like we literally came up with stuff that I still think of as magic. Like that's insane that we came up with all this stuff during this one time in human history. Like World War II really advanced like humanity by like thousands of years, it feels like. Like how long would humanity have gone without all these electronics if it weren't for the war? Like it really does feel like the war sped up human advancement like drastically. Maybe not, maybe we would have arrived at all these same technologies within the same time frame anyway, but it definitely feels like the war was the main driving force behind all these advancements.
Thus giving warning to the defenders of Britain, permitting anti-aircraft batteries to swing into action and RAF planes to rise for combat. Whenever Hitler's bombers attacked, at whatever altitude, from whatever direction, British interceptors were waiting for them.
Dang, that was a shot of a German plane just going down over England. Like that, even though we're not even learning about the war in this program, like all these war shots are just like, dang, that was real war taking place right there. Dang, and all these people on the roofs, see, that's crazy too. Like this is preserving people's mentalities during the war. Like all those people hiding on their roofs as the plane are passing by, like that's the motivation that people had to come up with these new technologies. Like people weren't just motivated to come up with this for fun's sake. It was literal fight for survival. I feel like that's what I need to communicate to you. It's like humans were pinned against the wall. Like entire human civilization was pinned against the wall by the Nazis. And the only way they got out was inventing the most incredible technologies ever. You know, you can even think about the war in the Pacific side of World War II as well. That was only ended from the nuclear bomb. It's just like no matter what, technology was the deciding factor in ending all of these conflicts. It's just, it really does expose something important about this era.
As a result, the Luftwaffe was blasted from the English skies and the tide of war turned.
Okay, now we've just been looking at the same kaleidoscope of glass tubes for like 20 seconds now. I don't know if this is the end or if we're just like taking a brief pause or something. It feels like they're going to come up with some sort of conclusion, but the music is just playing us off right now.
Yes, the electronic tube, in essence, is only a switch. But what a switch! It rectifies.
The electronic tube is only a switch, but what a switch. I guess that is a very fair statement. Probably like the most important switch we've ever figured out.
Amplifies, generates, controls, transforms light into electricity and back into light again.
I love how patriotic this also feels for some reason. Maybe it's just the music, but like I already am feeling like I'm marching in an army just listening to this. But I think that's part of the propaganda of this time is like you were supposed to feel like, you know, your army was the most advanced and your civilization was, you know, coming up with all these new technologies and everything. I feel like that's part of the design behind these sorts of film programs was to get the people who watched them to be patriotic, right? That was the whole point.
These tubes that look so mysterious are essentially simple in operation.
I honestly do love that they are just glass tubes that do look like very simple but also complicated. Like it does, even after watching this whole thing, it doesn't cease to amaze me. Like the capabilities of just these glass tubes, it really is. Like I really do feel like I've gained a new appreciation for electronics by watching this. Just like understanding the most basic fundamental elements of electronics, like you realize how they are really magic. Like I don't know, I hate calling them magic, but like they're just amazing is really what it is. They're amazing instruments and tools that we only just recently in human history figured out. I never really thought about glass tubes before this, but I really do appreciate them now. I really feel like I understand and appreciate them so much more than I ever did before this. And that being said, I don't even fully understand all of them, but I understand the impact of having these sorts of things in our society and in our technologies. You know, like this is really just a technological revolution we are seeing right now.
Incredibly rugged and sure in application. They open and close all forms of electronic circuits as swiftly as the lightning flash and as silently as the passage of time.
As quickly as a lightning flash and as silently as the passage of time. That's a pretty eloquent way of putting that as well.
In the world of today, they're helping us to win a war.
In the world of today, they're helping us win a war. Again, that is what is on the forefront of everyone's mind, is how is this technology going to help us win the war? Like, imagine trying to communicate to people that this glass tube that you're working on has the ability to, like, turn the tide of war. You know, like, that's what makes it seem so magic. Like, whatever crazy little light trick I came up with in this glass tube is going to, like, create a new machine that just defeats the enemy. It's just, like, it really is incredible.
In the world of tomorrow, they bid fair to lift all of us to new levels of achievement, comfort, and security.
It's funny because I feel like they're showing us all these different sorts of tubes, expecting the audience to be able to, like, recognize them based on what we just watched, but I'm just looking at these like I still don't really understand most of them. Like, I understand the concepts behind them, but, like, looking at them, it's impossible to tell what these tubes do just by looking at them. Or at least it's impossible for me to tell. Oh, okay, and that's the end. So this was produced by B.K. Blake Incorporated, and the animation was by Famous Studios. That's funny. And this was produced, by the Westinghouse Electric Manufacturing Company. So this is kind of like a commercial, right? Like, it's so strange because, like, they're definitely showing off the products that they make through this. So this is, like, pretty much a very long advertisement, but it's hard to understand, like, the context that this was created in, you know? Like, this could have been a commercial, but, like, did this air on TV? Like, where was this shown? I don't even know. Like, I always struggle with that question because this doesn't seem like a television sort of thing, especially not during the 40s. So I don't know where this would have been shown. It might have been shown in, like, movie theaters before movies or something. That just doesn't sound right either. I just don't think people would have wanted to watch a 20-minute program on electronics at work at the movies. I don't know. Maybe I'm wrong about that, but I don't understand the context in which this would have been shown. But no matter what, I really do feel like this was an effective piece of media. I feel like somebody from, like, 80 years in the future, still learned and gained a new appreciation for the technology that we have from this. Like, isn't that amazing? Like, I just learned so much about the stuff that I use every day from this, from 80 years ago. You know, it is incredible. I do think this was a really good watch. This is such a good blue video too. It's like, this is blue all over it. Oh, the very last frame of this is actually the Westinghouse logo, which I feel like is very interesting because this whole program, I didn't see this logo at all, but I have to imagine this logo must have been one of the most recognizable logos in America for a time, right? Westinghouse. The fact that I knew that name without knowing what they made or what their logo looked like just tells you this company used to be super big in America, probably the whole world. It's funny to see their icon or their logo be so unrecognizable. You know, like, I could show this to so many people and no one would recognize it, but I could say Westinghouse and I feel like more people would say, well, I feel like I've heard that before. But I definitely want to buy some Westinghouse products now. After watching this, I definitely believe Westinghouse was, like, on the cutting edge of electronics technology during this time. And I definitely would want to buy their products after watching this. In a sense, this is kind of like the best commercial ever because I did learn a whole lot from it. So I actually appreciate that. Thank you, Westinghouse, for producing this program to actually educate me on your products. I feel like this was very educational. I definitely learned a lot and I definitely gained a new appreciation for electronics, and I hope you all did as well. And if you did and you would like to help support me and this channel, you can follow the link in the description that'll take you over to the Internet Archive. The Internet Archive is where I get all these old programs from, so if you want to support me and what I do here, go donate to them. And with that, I think we're ready to cut to black.